This time, we're going to solve the circuit with a slightly different method. Yeah, we're still going to have to find the power of the circuit, but we're going to use the graphic method, which we have never seen before. So, what's the graphic method? Well, everything is going to become, pretty clear in just a second as I draw the circuit. But basically, you can actually, you may find a graph like a plot in the axis when you get a circuit. So next to the circuit, you get a plot within two axes. And you're gonna have to use that and solve the circuit using the graphic method. So let's just draw our circuit and the graph, which is given to us by the problem. So now, today, my circuit is going to be the following one. So I'm going to have a voltage generator and a resistance. And over here, two resistances. And then I'm going to have a net element, which I'm going to draw like this. And then down here we have this. And then the circuit is connected all the way down to this. So this one is my sorry, it's my R3, this is my R1, this is my R2, this is my plus minus V, and I'm gonna define the current flowing through here as my I. We also know this is the component, by the way. I going down here. We have this one, which is the component. Okay. And the graph is the following one. The IV characteristic of this component is can I get the red pen to work? Yeah, there we go. And then all the way up to this, and this one is 3. This value is 3. So what is the problem saying? Well, the problem is saying that for this non-linear circuit, so it's a circuit which has a non-linear element, we know that E is equal to 12 volts, R1 is equal to 1 ohm, R2 is equal to 1 ohm, and well, at R3 is equal to 2 ohms, and that the characteristic voltage current VI of the non-linear bipole is the one of the graph. find the power generated or absorbed by the non-linear bipole. Okay, so we have this circuit. The circuit is non-linear because it has a non-linear component, which is this bipole. And we know this characteristic voltage current of this bipole. Now, before we get into that, let's start with something relatively simple, which is the equivalent circuit of Thevenin at the two ends of the nonlinear bipole. So if I have to find the equivalent circuit of Thevenin at the ends, the two ends of the non-linear bipole. So let's start with this. Well, Thevenin equivalent circuit is, Thevenin basically says that each and every circuit, no matter how complex it is, can be actually simplified and represented by voltage source in series with a resistance. So we're going to have a voltage source, which we're going to call VTH, Thevenin, in series with a resistance, which we're going to call RTH, Thevenin. So let's find RTH first. RTH in this case is actually going to be R1 plus R2 all in parallel with R3. So we will have R1 plus R2 all in parallel with R3. So let's plug some numbers in here. Yeah, we know that E is 12 volt, R3 is 2 ohms, and those two instead are 1 ohm each. So 1 ohm and 1 ohm. So if we put numbers back into this, we have that we have basically 1 ohm plus 2 ohm all in parallel with 2 ohms. Oh, no. 1 plus 1, because those two are 1. So 1 plus 1 in parallel with 2. So RTH will be 1 plus 1, which is 2 in parallel with 2. So RTH is going to be parallel, so the product over the sum is 2 times 2 over 2 plus 2. So RTH will be 2 times 2 is 4. 2 plus 2 is 4. Those two cancel each other. And therefore, I get that RTH is 1 ohm. Now, I can also find VTH, so Thevenin, by saying, well, we're basically saying that is going to be R1 plus R2 times E over R1 plus R2 plus R3. So now, if I plug numbers back into this, I get that R1 is 1 plus R2, which is 1, times E, which we know is 12 volt, over R1, which is 1, plus R2, which is 1, plus R3, which is 2. So VTH is actually 1 plus 1 is 2 times 12 over 1 plus 1 is 2, 2 plus 2 is 4. So I can get rid of those. This becomes a 2, this becomes a 1. So I basically have that VTH is 12 over 2 which of course can be simplified as 6 over 1. So VTH is 6 volts. So we are done the first part, in which we have found the Thevenin resistance and Thevenin voltage for the equivalent circuit of Thevenin. So now you can actually say that in order to find the working point, we can actually use the graphic method. So I'm just going to plot the characteristic voltage current for the equivalent circuit of Thevenin, and I'm gonna find the vacuum and the short circuit points. So let me draw the Thevenin equivalent circuit first. The Thevenin equivalent circuit actually looks like this. We have a voltage source, as by definition, in series with a resistance. Then we will have this one which will be my point A, and this one which will be my point B, plus minus B. And this current flowing through here will be I. Now I can actually plot and make a graph of the characteristic voltage current for the equivalent circuit of Thevenin. I can say, okay, this point up here is going to be 6, and this point down here is going to be 6. So my characteristic, oh no, I'm going to use green, is going to be this one. Can I make a straight line? No, I can't. And it will be V given by VTH over RTH. Which in fact is just 6 over 1, which is 6. Now, I can say, okay, in the vacuum, I actually have the V2 is equal to VTH, which is equal to 6 volts, and I1 is equal to 0 amps. And in short circuit, I have that V is equal to 0 V. I1 is VTH over RTH. So as I said, 6 over 1, which is 6. Now, if I'm going to superimpose the two characteristics, I can get the working point of the double bipole. So if I'm gonna just superimpose this one and this one, I'm gonna get the working point of the double bipole. So I have I, V, those 2 points, which are 6 and 6. Whoops. So yeah, like this. And then I also have 3 and 3 of the other one. So I would have 3 and 3 of this other one, which would actually be like this, going up like this. There we go. So the problem is actually asking me the power generated or absorbed by the non-linear bipole. So the power is actually going to be, whoops, there we go. Come on, okay. So the power is actually going to be V times I, as by Ohm's third law. If I plug numbers back into this, it will be V times I, so 3 times 3. So the power will actually be 9 watts. And since it's positive, the power is absorbed. But anyway, yeah, it's positive 9, but the power is absorbed anyway, nonetheless. So yeah, this is how you solve a problem with the graphic method.